We'll now talk about the spaces. LP of omega. So as I already said earlier, omega in Rn, open set, and equipped with the Lebesgue measure. So the sigma X, the set is omega, and then the sigma algebra is a Lebesgue sigma algebra, and mu, the measure, is the Lebesgue measure. So such spaces, since the measure is fixed, so we concentrate on the domain instead, and we call these spaces LP of omega for 1 less than p less than equal to infinity. So we want to study the properties of these. These are very special. They occur in a lot of applications, and therefore let's go ahead. So proposition: let S be the set of all simple functions in omega, or defined on omega, sorry, which vanish outside a set of finite measure. Then S is dense in LP of omega 1 less than equal to p, strictly less than infinity. Okay, so what do you mean by a simple function? A simple function is a function phi of the form sigma I equals 1 to k alpha I chi of ei, where chi of ei is the indicator function or the characteristic function of a set E, which is 1 if x belongs to E, 0 if x does not belong to E. So we are saying here you can actually take the ei's disjoint, and the alpha i's are all real numbers. Okay, so we say that the function vanishes outside set of finite measure, means the measure of ei, that is the Lebesgue measure of ei, is less than plus in. Now mod symbol for a set will denote the Lebesgue measure, and therefore the measure of ei is finite for all I. That is what we mean by vanishing. So outside this, the union of ei, phi is 0, so it vanishes outside a set of finite measure. So such functions we claim are dense in LP of omega. So proof. Okay, so let phi belong to S. Then phi vanishes outside the set of finite measure, and what is the value? So mod phi power p is nothing but sigma mod alpha I power p chi of ei. So if you take integral phi power p dx over omega, this is equal to sigma I equals 1 to k of mod ei, which is finite. Okay, so therefore all these functions are in LP. Okay, so phi belongs to LP, 1 less than equal to p less than infinity. In fact, it's also in L infinity, because it takes only the values alpha I or 0, and therefore it's also in L infinity, but that's not relevant to this particular problem. So let f non-negative, fp integrable. Now any non-negative measurable function can be approximated by an increasing sequence of simple functions. So there exists phi n simple functions, 0 less than equal to phi n less than equal to f, and in fact phi n is monotonic, so it increases to f. So this means that automatically, since phi n power p is less than or equal to f power p. Everything is non-negative, so I don't have to put the modulus. So the integral is also finite. So this implies that phi n belongs to Lp of omega for all n. Okay. Further, mod phi n minus f is less than or equal to 2 times mod f, and therefore you put a power p, so you have 2 power p mod f power p. This one is integrable, and this one goes to 0 pointwise almost everywhere, and therefore by the dominated convergence theorem implies that phi n converges to f in Lp. So we have approximated f, in fact, by simple functions which vanish. Also, further, I forgot to say one thing. Since phi n is less than or equal to f, phi n is in Lp, and therefore this implies that phi n has to belong to S also. Because automatically, because if it did not vanish outside a set of positive measure and it's a simple function, then the integral will blow up. Okay, so phi n automatically belongs to S, and therefore we have approximated f by means of simple functions which vanish outside a set of finite measure. Now if f belongs to Lp of omega, you write f equals f plus minus f minus, the positive and negative part. So f plus is nothing but the max of f and 0, f minus is the minus the minimum of f and 0. So both are non-negative functions, and you have f equals f plus minus f minus, and mod f in fact is equal to f plus plus f minus. Okay. So then you have phi n, you have psi n, okay, phi n converging to f plus, phi n in S, this convergence is in Lp, and then you can have psi n which also converges in Lp to f minus by the psi n in S. So you put chi n equals phi n minus psi n, then chi n converges to f plus minus f minus equals f in Lp, and of course chi n belongs to S, and this proves the theorem. So we have found that anything can be approximated. So this leads us to an important theorem, which we will repeatedly use. Okay, 1 less than or equal to p less than infinity, omega in Rn open, then Cc of omega is dense in Lp of omega. So what is Cc of omega? So Cc of omega equals set of all f from omega to Rn R such that f is continuous and support of f is compact and contained in omega. So what is support of f? The set of all x in omega such that fx is different from 0, and then you have to take the closure. So it's a closed set always, and that set is, if it is a compact, then you say it's a continuous function with compact support. So these functions vanish outside a compact set. In particular, they vanish outside a set of finite measure. Okay, so that is these are functions, but they are not simple, they are continuous functions. Okay, so we want to show that these functions are dense in Lp of omega. Okay, so proof. So enough to show S that any phi in S can be approximated in the Lp norm by G in Cc of omega. because any f in S can be approximated by phi. If every phi can be approximated by G by the triangle inequality, you have that any f can be approximated as closely as you like by function G. So let phi belong to S and let epsilon be greater than 0. Okay. So then by Lucin's theorem, so this is a theorem in analysis which say in measure theory, so we say there exists G in Cc of omega, so it's a continuous function with compact support such that G equal to phi except possibly on a set of measure less than epsilon. Okay, so function, measurable function in S is almost like a continuous function with compact support. Namely, you can make it equal to a continuous function with compact support, with failing except only where you fail, that will be a set which is a very small measure. And further, norm G infinity, its sup norm is less than or equal to norm phi infinity, which is also, phi is also in L infinity, as I said, remarked earlier, and therefore you have this. Okay, so then what do you have? You have integral on omega mod G minus phi power p dx is what? Is less than or equal to, so norm G is less than or equal to norm phi, so this is equal to 2 power p norm phi infinity power p, that will all come out. Then you have measure, you won't have measure of omega because G equal to phi except on a set of measure 0. So this function is 0 except it's non-zero only on a set of measure less than epsilon. So that measure will come here. So this is less than 2 phi epsilon, and therefore this shows that Cc omega is dense, approximates S in LP in the sense I mentioned above, and hence Cc of omega is dense in LP. Remark, in fact we can say d of omega, which is C infinity functions with compact support in omega. This is a much smaller set. Cc omega is bigger, C infinity you want them to be infinitely differentiable. This is also dense in LP of omega, but this requires more sophisticated tools from analysis like convolution and so on, and we will not prove it in this place. Okay, so next corollary. Let omega contained in Rn be open. Let 1 less than or equal to p less than infinity. Then LP omega is separable. That means there exists a countable dense set. Okay, proof. So Weierstrass theorem says, so Weierstrass what does it say? So if G belongs to Cc of omega, then on support of G, which is a compact set, we can approximate G uniformly, that's in the L infinity norm, by a polynomial, and hence by a polynomial with rational coefficients. So if P is such a polynomial with rational coefficients and you have G minus P, infinity is as small as you like, then on support of G, you outside the support G is 0, you put P also to be 0, so you get a LP function, all right, because it's continuous in the support, and outside it's a closed set and outside it is 0. That's fine. The support is of compact and therefore it has finite measure, therefore this function P is in LP. So this will also imply that norm G minus P in LP is small, less than the epsilon times the measure of something and so on. So it will be is also small, and therefore notice that polynomials with rational coefficients on a compact set is a countable set. Okay, so now we write omega equals union n equals 1 to infinity omega n, where omega n is omega intersection b0 n, the ball in Rn with center origin and radius n. Then you have that omega n is bounded and therefore omega n closure is compact. Okay. Now let epsilon be greater than 0 and f belong to LP of omega. Okay, that means we take a representative which is a P integrable function. Then you have, there exists a G in CC of omega such that norm f minus G in LP is less than epsilon. So let K be the support of G, compact. Okay, so then we can find a polynomial. So there exists P, capital P, polynomial with rational coefficients such that for all x in omega n, we have mod gx minus p of x is less than epsilon by mod omega n power 1 by p, and therefore this implies that norm G minus capital P. Now you put P equal to 0 outside omega n, then P will become a LP function as I explained earlier, and you will have norm G minus P in small l in LP is less than epsilon by the choice. Okay, because outside omega n everything is 0 and inside it is less than epsilon by this, so just the measure will get multiplied. Okay, so therefore you have norm of f minus P is less than 2 epsilon. So you can always find a polynomial with rational coefficients with on a compact set such that this is okay. So what is n here? So this K is supportive, then this is contained in omega n for some n, because K is a compact set, it is closed and bounded, and therefore it has to be inside one of the omega n's. Okay, so that is the n which we are taking here. Okay, so now you take phi n equals polynomials with rational coefficients in omega n closure and 0 outside. So this is a countable set, and therefore union phi n is countable, and we have just seen it is dense in LP, and therefore LP is separable. Okay, so this is the proof of this important corollary, which says that all the LP spaces other than L infinity are separable. So what about L infinity itself? So proposition omega contained in Rn, open set, then L infinity omega is not separable. In fact, we will show there is no countable dense set. Okay, so that's what we have to show. Okay, so proof. So let X belong to omega. So then you have Rx positive such that B of X Rx is also contained in omega. There will be a ball which will contained in omega. So let us take phi sub x to be the function which is the characteristic function of this ball. Okay, and now I am going to define u of x. So this is equal to set of all f in L infinity of omega such that f minus phi x norm is strictly less than half. So this is open ball in L infinity omega, center phi x, radius half. Okay, so this are all open sets. So you have a collection ux, x in omega is an uncountable collection of open balls. Now what if x is not equal to y? Then you look at phi x minus phi y. What are the possible values it can take? It can take the value 0, of course, if x, if the point where you are evaluating it lies outside both these balls, bxrx and byry, or it can take 1 or minus 1 because if it's in one ball and not in another. If it is in both the intersection of the two balls, then it will be 0. So it will be 0, 1 or minus 1. Therefore norm phi x minus phi y infinity is always 1. Okay, and therefore so this implies that ux intersection uy is empty, because if f belongs to ux and f belongs to uy, then f minus phi x is less than half, f minus phi y is less than half in the L infinity norm, and by the triangle inequality norm of phi x minus phi y will be strictly less than 1, less than or equal to these two, which is strictly less than 1, which is a contradiction because we know it is equal to 1. Okay, so ux intersection uy is empty. So if Fn is a countable set in L infinity, it can meet at most countable number of ux's, because a particular ux fn can belong to only one of the ux's, it can't belong to two of them. Okay, so each fn will belong to one ux. So if you take all the ux's which contain these fn's, they will be countable in number. Okay, and therefore there will be several sets which do not meet ux. So this implies fn is not dense, because several ux's, that's an uncountable collection, will be left out. They won't meet this set at all, and therefore no countable set is dense in L infinity, and therefore L infinity cannot be separable. Okay, so that is, we have shown that, studied the separability of the thing. We saw the reflexivity of some of the LP spaces, and so now we are going to